Hi and Assalamualaikum. So I will explain about the calculation for question number 1. Okay, question number 1. Show that fx equals to square root of x on the interval from 0 to infinity, close at 0 and open at infinity, is uniformly continuous on this interval but does not satisfy the lipstick condition on the interval from 0 to infinity, close at 0 and open at infinity. Okey, untuk soalan ni kita pecahkan kepada 2 part. Part 1, prove uniform continuous, and part 2, show it is not lipstick. Okey, for part 1, step 1, start with the definition. For every epsilon greater than 0, there are exists delta greater than 0 such that modulus fx minus fy less than epsilon whenever 0 is less than absolute value of x minus y and this is less than delta. So, we proceed to step 2. Step 2, use the function fx equals to square root of x. We want to look at the distance between function value. So, modulus fx minus fy equals to modulus square root of x minus square root of y. This expression is not so easy to work with directly. So, we square root both sides and then we get this. How do we get from this to this? We start with the difference of square root this. To make this easier to work, we square root both sides and then use the algebra identity and we get this. So, we apply it to our expression. So, kita gantikan function kita dalam ni. And then, bila kita dapat macam ni, dia macam susah untuk kita kira. Jadi, cara yang lebih senang, kita guna identity. So, kita guna identity, kita dapat yang ni. And then, yang ni multiply. Bila pergi sini, dia akan jadi bahagi. Okay. Bila dalam bentuk macam ni, kita square root both side. And then, yang ni dengan yang ni kita boleh potong. Sebab tu lah dapat macam ni. Okay. Bila dah dapat bentuk macam ni, jangan lupa letak less than epsilon. Okay, so let's proceed to step 3. Step 3, choose a delta in the terms of epsilon. Now, I choose delta equals to epsilon square. Modulus x minus y less than delta. Delta ni kita ganti dengan epsilon square. Bila epsilon square, kita pergi belah sana, dia akan jadi square root. And then kita dapat bentuk dalam ni. Bila kita dapat bentuk dalam ni, maksudnya kita dapat epsilon je, the condition is satisfied. So, kita boleh buat conclusion kat sini. Since we were able to find a delta equals to epsilon square, this work for all epsilon greater than 0, the function fx equals to square root of x is uniformly continuous on the interval from 0 to infinity, close at 0 and open at infinity. So, let's proceed to part 2. Okay, for part 2, show it is not lipstick. Okay, step 1, start with the definition of lipstick. A function f from the set E to the real number is lipstick continuous if there exists a constant k greater than 0 such that modulus fx minus fy less than equal to k modulus x minus y for every x and y are element of E. And then we proceed to step 2. Step 2, assume the function of fx equals to square root of x is lipstick. So, we let y equals to 0 and x greater than 0. So, for y equals to 0, kita gantikan dalam function ni. And then, kita akan dapat macam ni. Bila kita dapat macam ni, kita boleh divide by x. Kita divide kiri dengan kanan dengan x. Lepas tu, kita akan dapat k greater than equal to 1 over square root of x as x to positive 0, then 1 over square root of x to infinity. Hence, as 1 over square root of x become arbitrarily large when x to 0, there is no constant k that can satisfy the inequality for all x greater than 0. So, we conclude the function fx equals to square root of x is uniformly continuous on the interval from 0 to infinity, closed at 0 and open at infinity, but it does not satisfy the Lipstick condition.
Now I will explain question 2. Let M1 row 1 and M2 row 2 be two matrix spaces. Suppose F is continuous on M1 and F is a closed subset of M2. Prove that F inverse F is a closed subset of M1. So based on theorem 5.2.5, it states that F is continuous on M1 if and only if F inverse G is an open set in M1 when G is an open set in M2. So to answer the question, we let F subset M2 be a closed set as it stated in the question. So then the complement FC is open in M2. Since F is closed in M2, that means its complement FC is open in M2. So based on from theorem 5.2.5, since F is continuous, from this we can apply to complement F, which is open. Since F is continuous, then F inverse FC is open in M1. So the properties of inverse image is this. Then we can say that the complement of F inverse F is open in M. Thus, we can conclude that F inverse F is closed in M1.
So for question number 3, we have to prove two sides, which is the left side to the right side and also the right side to the left side. And the first one is, suppose function is continuous on metric 1 and let F be a closed subset of M2. And here we want to show that inverse of F is closed in M1. Since F is closed in M2, its complement, which is the FC, is open in M2. Since function is continuous, then inverse of FC is open in M2. So by properties of inverse image, inverse of FC is equals to inverse of F and its complement. Therefore, the complement of inverse F is open in M1, which means the inverse of F is closed in M1. And the next one is from the right side to the left side. We suppose that inverse F is closed in M1 whenever F is closed in M2. And we let G be an open subset of M2, then GC, which is the G complement, is closed in M2. By our hypothesis, inverse of G complement is closed in M1. So by properties of inverse image, inverse of G complement is equals to complement of inverse G. Therefore, the complement of inverse G is closed in M1, which means the inverse of G is open in M1. Since the preimage of every open set is open, then function is continuous.
In this video, I will explain question number 4, which is, if A is closed subset of a compact matrix space M row, prove that the matrix space A row is also compact. So, we are given that M is a compact matrix space and A is a closed subset of M. To prove A is a compact, we must show that every open cover of A has a finite subcover. So, let the collection of open set alpha indexed by alpha in I be an open cover of A. I can be any set. This means that all open set alpha are open in A and their union covers A. Since A subset M, there exists some open set in M such that each open set in the cover of M can be rewritten as the intersection between an open set in M and the set A. Then we have this. It means that the collection of open set in M almost covers but not all of M. Next, using the closeness of A, its complement M set minus A. This means it is the part of M that is not in A is open in M. So, the collection of P sub alpha for alpha in I union with the set M minus A is an open cover of M. It means this is the open cover of M we are constructing in the proof, or the collection open set in M is cover A, and M set minus A cover the rest of M. So this union covers all of M. Since M is compact, this cover has a finite subcover. So there is subset alpha 1 until alpha n such that M is a subset of B sub alpha 1 union up to B sub alpha n union with M set minus A. Now we intersect both sides with A, then we get this. So U alpha 1 up to U alpha n is a finite subcover of A. Therefore, every open cover of A has finite subcover, which means that A is compact. So we have proven that if A is a closed subset of a compact matrix space, then the matrix space A rho also compact.
Lastly, for question 5, suppose f is a bounded function you find on a closed bounded interval AB. If f is Riemann integral on AB, prove that for every epsilon greater than 0, there exists at least one partition P such that absolute value UFP minus LFP is less than epsilon. F is Riemann integral if and only if the upper integral and lower integral are equal, and we write this as I star of f equals to I sub star of f, where I star of f is the infimum of all upper sums of f in respect to partition P, and I sub star of f is the supremum of all lower sums of f with respect to partition P. Since I star f equals to I sub star of f, we denote this common value as capital I, where capital I is the integral from a to b of fx dx. By definition of infimum, for all epsilon greater than 0, there exists a partition P1 such that UFP1 is less than I plus epsilon over 2. By definition of supremum, for any epsilon greater than 0, there exists a partition P2 such that LFP2 is greater than I minus epsilon over 2. Therefore, the difference between the upper and lower sums is less than I plus epsilon over 2 minus I minus epsilon over 2, which this will simplify to epsilon. So we have shown that for every epsilon greater than 0, there exists a partition P such that the difference between the upper and lower sums is less than epsilon.